Hello, and welcome to Chemistry 103. Last time we talked about chemical bonding in the context of ionic compounds, which involve a transfer of electrons from one atom to another in order to create stable noble gas configurations on both atoms, which then obtain a charge and stick together via electrostatic forces. Today, we're going to continue our discussion of compounds by introducing the idea of a covalent compound. Covalent compounds involve bonds between two nonmetals, as opposed to ionic compounds, which occur between a metal and a nonmetal. The covalent bonds can occur between elements that are similar to one another, such as other nonmetals. They can also occur between identical atoms. Some such elements that bond with themselves are nonmetals such as oxygen, bromine, and nitrogen. Another thing about nonmetals is they tend to gain electrons rather than losing them. This is because gaining electrons is the easier route towards gaining a noble gas electron configuration, whereas for metals, as we learned last time, lose electrons to go down to the nearest noble gas electron configuration. The main difference between covalent compounds and ionic compounds is that electrons are shared between atoms and not transferred. So this allows these molecules to exist freely as isolated particles. The simplest covalent bond occurs between two hydrogen atoms. Now, as we discussed before, the hydrogen atom has one 1s electron, and if it obtains another electron from another hydrogen atom, both hydrogen atoms obtain the nearest noble gas configuration, which is helium. The noble gas configuration of helium, of course, is two electrons which are paired together of opposite spins in the 1s orbital, and when the two hydrogen atoms come together, the electrons will acquire opposite spins from one another and exist in the space between the two hydrogen atoms as they pull close together, as shown here in this diagram. And this structure is lower in energy than the two hydrogen atoms being free in space. This is known as diatomic hydrogen or molecular hydrogen, and it is pretty widely used in chemistry due to its high reactivity. Now, for larger atoms, we begin to talk about something called an octet. So this is when there are 8 valence electrons around each atom that exist in the molecule. We can talk about this in terms of a number of diatomic molecules of identical atoms in which the atoms share valence electrons with each other. Now, each atom in a molecule will seek to obtain the nearest, most stable noble gas configuration, and in order to do this, the formation of single, double, or triple bonds may occur. As you can see here, there are 3 examples on the bottom. We have 2 fluorine atoms. Fluorine atoms each contain 7 valence electrons because they are in group 7 of the periodic table. When they come adjacent to one another, then the unpaired electron on each fluorine atom pairs with the unpaired electron on the other fluorine atom, and the fluorine atoms become close together, and the bond exists in the space between them, consisting of those paired electrons. The rest of the electrons form what are known as lone pairs on the fluorine atoms themselves. You see in the middle is oxygen. Oxygen has 6 valence electrons, and in order to form bonds with itself, 2 of those unpaired electrons on each oxygen bind with two of the unpaired electrons on the other oxygen atom, forming a shared double pair of electrons that exists in the space between the oxygen atoms. And lastly, for nitrogen, nitrogen has 3 unpaired electrons in its valence shell and can gain 3 electrons in order to obtain a noble gas configuration. And so when it binds with itself, each of those 3 valence electrons binds with a unpaired valence electron on the other nitrogen atom, and they form what is known as a triple bond in the space between the nitrogen atoms. So, this diagram shows the atoms that form diatomic molecules with themselves, the simplest one being hydrogen, which we discussed. And then there is nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, which all form diatomic molecules, which achieve an octet of electrons in their valence shell. Hydrogen atoms obviously don't achieve an octet, but a duet because they only have 1 electron each. When it comes to binding non-identical nonmetal atoms, you have to start thinking about how many electrons each atom needs to obtain an noble gas configuration or complete the octet. So you have to account for the number of vacancies and unpaired electrons in each valence shell, and each of these unpaired electrons can be used to form a 2-electron bond with another atom. And then when you have established which electrons participate in bonding, you will share each electron between the atoms that a bond is forming between, and each of these atoms will then obtain a noble gas configuration. And we'll go through this a bit, but here's an example shown in this diagram of the methane molecule. You have carbon in the center, which has 4 valence electrons, and then you have 4 hydrogens, each of which has 1 valence electron. So each valence electron in the hydrogen pairs with one of the valence electrons in the carbon, and the carbon achieves the octet because now it has 8 electrons in its shell, and the hydrogens each in turn obtain a duet because they now each have 2 electrons in their shell. The entire molecule is neutral and stable. Now, talking about electron configurations, it's easier to talk about them in terms of something called Lewis structures. So Lewis structures are diagrams that show where all of the valence electrons are in a molecule. We start by representing elements by their chemical symbols from the periodic table. So C for carbon, Cl for chlorine, and it's onward and upward. Shared electrons in a Lewis structure are represented by covalent bonds, which are a line between 2 atoms, and a line represents 2 shared electrons. Unshared electrons are called lone pairs and are represented by pairs of dots. 1 dot represents 1 electron, 2 dots represents 2 electrons, and so on. Two electrons in general are stable together, whereas 1 electron will try to form a bond. So we're going to go through this, drawing electron dot formulas. So let's start with fluorine. So the atomic symbol for fluorine is F, and it forms a diatomic molecule with itself. It has 7 valence electrons. So you see here there are 3 sets of paired dots, which represent 6 paired electrons, and 1 single dot, which represents an unpaired electron. And then you have a second fluorine atom, presumably with an electron of opposite spin. And what happens is the unpaired electrons are attracted to each other because they have opposite spin, even though they repel each other a little bit. They attract each other enough to exist in the space between the fluorine atoms and pull them together, which leads us to draw a bond between the fluorine atoms. This bond is a pair of electrons that form a bond pair and are shared by the two atoms. The rest of the electrons are lone pairs which repel one another and stick off in opposite directions from one another off of the atom. And they are not involved in bonding. So, to draw Lewis structures, first you count the number of valence electrons for each of the elements, and then the total number of electrons need to be represented in your Lewis structure. If you have something that is positively or negatively charged, you have to add electrons if it's negatively charged and subtract electrons if it's positively charged. Then you need to establish the central atom and draw single bonds to all of the surrounding atoms, and then add lone pairs to each atom to make sure that it counts up to 8 on each atom, or 2 for hydrogen. And as long as everything meets the octet rule and the number of electrons matches the number of valence electrons in each atom, plus or minus the charge, then the structure is correct. Now, this may sound a little confusing at first, but we will go through it. So, picking the central atom. If you have 3 or more atoms, the central atom usually appears only once in the formula and is often listed first. Another handy trick is that hydrogen is always a terminal atom because it only needs 2 electrons and can therefore only form 1 bond. Here is an example. Ammonia, or NH3. Nitrogen is in group 5, so it has 5 valence electrons. And hydrogen has 1 valence electron, and there are 3 of them, which means that the total number of electrons in the molecule is 8. And since nitrogen comes first and hydrogen can only form 1 bond, the nitrogen is the central atom, which is indicated here, and each hydrogen binds once to the nitrogen. Now, if you were to count up the number of electrons represented by those bonds, it is 6. So we are missing 2 electrons from this structure, which means that we place the remaining 2 electrons on nitrogen, which adds up to a total of 8. So there are 3 hydrogens and 1 lone pair on the ammonia atom, or molecule. Now, a similar molecule is NF3, or nitrogen trifluoride. Once again, nitrogen has 5 electrons, valence electrons anyway, and fluorine has 7, so 3 of them have 21, for a total number of electrons of 26. Once again, nitrogen is the central atom, and we draw a bond between the nitrogen and each of the fluorines, which accounts for 6 of the electrons. As before, we put 2 electrons on nitrogen, so it has 8 around around it, and we place 6 around each of the fluorine atoms, bringing the total number of electrons surrounding it to 8 as well. And so we have achieved the octet on all 4 atoms, and this is our molecule. Now, we're going to talk about double bonds. So sometimes you have more valence electrons than single bonds can account for. For instance, in the case of carbon dioxide or CO2, if you draw CO2 with just single bonds, you will end up with too many electrons in your Lewis structure. In this case, you may have to add double bonds to reduce the number of lone pairs. And we will go over how to do this. So, in general, if you erase a lone pair from each of two adjacent atoms and draw a bond between them, that will account for 2 electrons. Now, it's important to remember that each atom still meet the octet rule, but when you draw a double bond, or when you draw a second bond, then that reduces the number of electrons in the diagram by 2. So carbon dioxide. Carbon has 4 valence electrons, and oxygen has 6, so 2 of them have 12, bringing the total number of electrons to 16. If you draw the single bonds and fill in the rest of the valence electrons with lone pairs, you end up with 20 electrons, which is more than 16 and therefore wrong. If you draw one double bond between a carbon and an oxygen atom, you eliminate 2 electrons from the structure while retaining the octet on both oxygen and carbon. However, you still have 18 electrons, which is 2 too many and therefore wrong. If you draw a second double bond between the carbon and the second oxygen, you remove another 2 electrons from the Lewis structure while maintaining the octet on all atoms. And this structure has 16 electrons, which is the right number of electrons, and therefore this is the structure of carbon dioxide. Carbon dioxide is a fairly stable molecule because it has 2 double bonds in it, which is why it's a product of combustion reactions where you burn fuel and produce carbon dioxide and water. So now we're going to draw some electron dot formulas to demonstrate these principles in as exhaustively a manner as possible. Starting with NH4 plus, or ammonium. So first we need to determine the arrangement of the atoms. Now, from what we learned before, we can deduce that the nitrogen is the central atom and that the hydrogens are terminal atoms. And since hydrogens each form 1 bond, we can guess that they all form a single bond with the nitrogen. Nitrogen additionally has 5 valence electrons, and there are 4 valence electrons contributed by the hydrogen. However, the ion is positively charged, so we remove 1, which brings the total number of electrons to 8. As I said before, we can draw single bonds between each of the hydrogens and the central nitrogen, which, if you remember, each single bond accounts for 2 electrons. So 2, 4, 6, 8. The total number of electrons in this structure is 8. And just for good measure, we put it in brackets and put a little plus sign next to it to indicate that it is a singular unit that is positively charged. In this case, the positive charge rests mostly on the nitrogen atom. Here is another molecule. This one's a little more complicated. It is the sulfate ion, SO4 2-. In this case, we're going to determine the arrangement of the atoms. So sulfur comes first, and there are 4 oxygens, making it fairly easy to deduce that sulfur will be the central atom. And sulfur has 6 electrons, as do each of the oxygen atoms, bringing the total, adding 2 electrons for the charge of -2, brings the total electrons to 32. And sulfur is central atom surrounded by the 4 oxygens. Now, we start by forming single bonds between each of the oxygens and the central sulfur atom, which leaves 8 electrons around sulfur, but only 2 on each of the oxygen atoms. and then we put lone pairs around all of the oxygens, bringing the total number of electrons around each oxygen to 8, meaning we have completed the octet on all atoms, and the total number of electrons represented is 32. Now, this ion has a negative charge, so we put it in brackets and put a 2- next to it to indicate that the whole molecule has a net negative charge. Now, carbon monoxide, or CO. This one seems like it would be pretty simple. We determine the arrangement of the atoms. There really is only one arrangement for the atoms because it's only 2 atoms. And we know that carbon has 4 electrons because it's in group 4. And we know that oxygen has 6 electrons because it is in group 6. Which means that the total number of valence electrons is 10. Now, it's easy to see that there will be too many electrons, and we will probably need multiple covalent bonds in order to account for them. So, here is the carbon atom and the oxygen atom. If we form 3 bonds between carbon and oxygen, that is a total of 6 electrons, and then if we add 2 electrons or 1 lone pair to each atom, that's 8 electrons on each atom and a stable electron configuration. If we had only a single bond, then there would be 2 lone pairs on each of the carbon and oxygen, which would be a total of 16 electrons. I'm sorry, 14 electrons. All right, now here is a slightly more complicated one, the thiocyanate ion, or SCN-. This was in our lab, if you have done that at this point, lab number 5. So, determining the arrangement of the atoms is a little bit difficult in this one, but we were given the hint at the beginning that carbon is the central atom. So, sulfur has 6 electrons in its valence shell, carbon has 4 electrons, and nitrogen has 5 electrons. So we also have a negative charge, so we add an electron, bringing the total number of electrons to 16. Now, if we can't complete the octet on an atom, then we have to form multiple covalent bonds in order to achieve the octet. So, carbon being the central atom, you form 2 double bonds, one between carbon and sulfur, the other between carbon and nitrogen. This puts an octet on carbon, and then if you add 2 lone pairs to each of the sulfur and the nitrogen, they have an octet on them as well. And then you put it in brackets and indicate the negative charge, and that's your molecule. Now, sometimes there will be multiple options about where to put a double bond because there will be a number of identical possibilities. In reality, all of these structures exist and flip back and forth spontaneously, and this phenomenon is known as resonance. So it's a thermal effect of quantum mechanics that the structures will randomly switch between each other. Each of the individual structures is known as a resonance structure, and we will start by examining the nitrate polyatomic ion, NO3-. There's also ozone, which is slightly different. It is a bond between 3 oxygen atoms, which has 2 possible resonance structures. So, example 1, nitrate. So, first of all, you can draw nitrate like this. You have nitrogen in the center, 3 surrounding oxygen atoms, and you account for the disparity in the number of valence electrons by adding a double bond to one of the oxygens. However, there are 3 oxygens that are identical, and so you can also draw it this way, and you can also draw it this way, with the double bond going to each of the individual oxygen atoms. And these structures are all identical. Now, in this case of ozone, or O3, ozone has 18 valence electrons, 6 for each of the oxygen atoms. Now, you can account for this either by placing a double bond between this oxygen and the central oxygen, or by placing it between this oxygen and the other oxygen. And since these are equivalent, they exist simultaneously in equal distributions in all samples of ozone. And they are indistinguishable from one another, so they are often drawn in this way, which has a little dotted line indicating that both structures are equally valid. And in fact, we find that the electron density is shared in such a way that these bonds are sort of like 1.5 bonds each. So those are the resonance structures, and this is the hybrid structure. Here's another example, the benzene molecule. So benzene is a ring of 6 carbon atoms with a terminal hydrogen on each carbon and a double bond between alternating carbons. So you see here, there's a double bond, a single bond, a double bond, a single bond, double bond, a single bond. Now, you can also draw it equivalently with this double bonds and single bonds switched. And in organic chemistry, you talk about this a lot, and you often use a circle to represent the resonance structures of benzene. Now, there are also a number of exceptions to the octet rule. One of them is boron. Boron only has 6 electrons around it when it's bonded for most of the time, because it only starts out with 3 valence electrons, and losing those valence electrons is very energetically unfavorable. Gaining 5 electrons is also very energetically unfavorable, so boron often settles for just pairing its 3 electrons with 3 other electrons, forming molecules such as BH3 or BF3. Another thing that can happen in period 3 or below is that molecules can exceed the octet rule. Things like sulfur or phosphorus can have more than 8 electrons on the central atom. This is because the d orbital electrons and d orbitals participate in the bonding structure and allow for more combinations and possibilities. We will examine this a bit when we talk about SF6 and PF5. So, here are the pictorial representations of the exceptions to the octet rule. We have BH3 here. It only has 6 electrons around this boron atom. And BF3 here. The fluorines have an octet, but boron does not. And then here is sulfur hexafluoride. The fluorides each have 8 electrons, but the sulfur has 12. And then phosphorus pentafluoride. There are 10 electrons on the phosphorus, but only 8 on each of the fluorines. Now that we know how to draw these compounds, we can start thinking about naming them and writing their formulas. So the simplest ones are molecular binary compounds, which are composed of 2 nonmetal elements. And we name these by using the full element name for the first nonmetal and adding the "-ide" ending to the full name of the second nonmetal. So the second nonmetal is named like the binary nonmetal in binary ionic compounds, or like the anion, such as chloride or fluoride. And then you indicate the number of atoms by adding the numerical prefixes that are based on often the Greek or Roman numbers. There's a table given in your book that we'll talk about in a second. But here they are again. 1 is mono, which is usually omitted. Di is for 2, tri for 3, tetra, penta, hexa, and so on and so forth. In ionic compounds, subscripts are not mentioned in the name, so if you have something like an Na2O, you don't say disodium oxide, you say sodium oxide. Or barium chloride, it's not barium dichloride. Sodium sulfate is sodium sulfate, not disodium sulfate. However, many compounds can exist for many pairs of nonmetallic elements, and therefore you have to specify which ones you mean. Nitrogen and oxygen is a good example. You can have NO, you can have NO2, you can have N2O. NO is called nitrogen monoxide. NO2 is nitrogen dioxide. N2O is dinitrogen monoxide. All unique names for unique molecules. Now, naming, so adding the prefixes will sometimes cause two vowels to be adjacent to one another. So if you ever have an O or an A that appear next to one another, you replace one with you drop the first one and keep the second one for ease of pronunciation. For example, dichlorine monoxide is not monooxide, it's monoxide. Or tetraphosphorus hexoxide, it's not hexaoxide, it's hexoxide. Here's more examples. Iodine pentafluoride, diboron trioxide, and nitrogen trioxide. More examples: arsenic trichloride, carbon dioxide, and carbon monoxide. These are summarized in table 6.3.1 or on page 141 of the OER textbook. You should know these prefixes. They're pretty standard, and you're going to be asked to distinguish between them. And then when you're writing the chemical formula based on a name such as dichloro, you use the symbols as they appear in the name in the same order. So you don't put the second element first, because that will be confusing. And then use the prefixes to identify the appropriate subscripts. So here's a flowchart for naming chemical compounds. It's helpful to distinguish between metals and nonmetals, because metals, when a metal bonds to the nonmetal, it forms an ionic compound. A molecular or covalent compound is formed between two nonmetals. So in the case of ionic compounds, the cation is the metal, or in some cases ammonium, and then the anion is a nonmetal. You determine whether the cation forms only one positive ion or if there's more than one possible. Then if you have only one possible positive ion, you just use the name of the element, or ammonium in the case of ammonium salts. And then if there are more than one possible positive ion, you use the element name followed by a Roman numeral equal to the charge. For the nonmetal, you either have a monatomic ion or a polyatomic ion. If it's a monatomic ion, you use the first syllable of the element name followed by "-ide". And for the polyatomic ion, you just use the name of the polyatomic ion. In the case of molecular compounds, you have the first nonmetal followed by the second nonmetal. And in the case of the first nonmetal, you use a prefix to match the subscript before the element name. And for the second nonmetal, you use a prefix to match the subscript and add "-ide" at the end. Another type of molecule is acids. These produce H+, when dissolved in water. H+ is a proton, a positively charged hydrogen atom. And these acids are generally composed of an H+ cation and an anion, such as a halogen anion or an oxyacid or an oxypolyatomic ion. And then, so in the case when it's a nonmetal anion and H+, it's called a binary acid, and then an oxyacid has H+ and a polyatomic anion, usually containing oxygen. So, we name binary acids by using the prefix hydro before the root, and then adding the suffix "ic" and the word acid to the root name. So, for example, HCl is hydrochloric acid because it has chlorine in it, and then HI is then hydroiodic acid. Oxyacids produce H+ and a polyatomic ion when dissolved in water, and they're generally composed of hydrogen, oxygen, and some other nonmetal. In the case of naming these, you use the root name of the polyatomic ion. If it ends in "ate," you use the suffix "ic." If it ends in "ite," use the suffix "us," O-U-S. So, for instance, H2SO4 from the sulfate ion is sulfuric acid. And then H2SO3 from the sulfite ion is sulfurous acid. Now, this brings us into molecular geometry. So up to this point, we've talked about the electron configurations, but we haven't talked at all about the structure of these molecules and what they look like in three-dimensional space. If we look at the methane molecule, CH4, you can see that if we have the hydrogen bonds pressed into a flat plane, then there's a 90-degree angle between them, and they are a bit cramped together, and there is empty space above and below the plane. This doesn't seem like it would be the most stable configuration. We'll talk a bit about how these electrons and bonding atoms interact with one another to make the shapes of different molecules. In order to do this, we have to talk about something called the Vesper theory, which means valence shell electron pair repulsion. It treats electron pairs as being distinct units that repel one another, and it talks about the way that the repulsion affects the shape. So bonds have electrons in them, ion pairs have electrons in them. Electrons are negatively charged. Charges that are alike to one another repel one another, and this repulsion affects the shape. The simplest shape of a molecule is linear. Things like HCl are linear because there's only two atoms, and carbon dioxide is linear because of the two double bonds on the carbon atom. This forces, due to electron pair repulsion, for the oxygens to be as far away from each other as physically possible, which is on opposite sides of the carbon atom. Another simple structure is trigonal planar, like a triangle. This structure is flat, and there is a 120-degree angle between the atoms bonded to the central atom. Something like formaldehyde, which is H2CO, this double bond with oxygen has a large amount of electron density, which repels the electrons in the two hydrogen bonds and forces them, which also repel each other, and they force themselves away in equally and opposite directions to balance the repulsion forces equally. Another slightly more complicated structure is the tetrahedral structure, which is where you have a central atom surrounded by 4 other atoms. In this case, the repulsion of the electrons leads to the adoption of this 4-pointed pyramid. And instead of having a 90-degree angle between the atoms, you have instead a 109-degree angle, and the hydrogen atoms pop into 3-dimensional space. So you can see here, it's hard to represent this in 2 dimensions, but you see this dark triangle shows a hydrogen atom coming out of the page, and this hashed triangle shows the hydrogen atom going into the page. And in this way, we maximize the stability of this atom. And this is the methane atom from before. As we get into more complicated molecular structures, we have to start adopting even more complicated arrangements. So if you have 5 atoms around the central atom, which you can have in the case of something like phosphorus pentachloride, you will have something known as the trigonal bipyramidal arrangement. So you have a trigonal planar central plane with the atoms separated by 120 degrees, and then you have a line going up the middle which forms a 90-degree angle with the central plane, which forms 2 pyramids facing in opposite directions. Then you have octahedral geometry, where you have 6 atoms around the central atom, such as sulfur hexafluoride. This is when you have 90-degree bond angles in every direction. Here is shown 2 fluorines going backwards into the page, 2 fluorines coming outward and out of the page, and then a fluorine on top and a fluorine on bottom, and a 90-degree angle between all of them. Now, you may have been asking yourself, what about the lone pairs? So, a good example of this is the water molecule. What is the bond angle between the hydrogen atoms in water? Because we might be tempted to think that it's a linear molecule because there are 2 hydrogen atoms, they repel one another, and then they must go to opposite ends. But there are also 2 lone pairs on the oxygen. We set the molecule up. We have our 2 single bonds between hydrogen and oxygen, and then our 2 lone pairs. The lone pairs repel each other, and the bonds also repel each other. And if we count the total number of pairs, there are 4 pairs. So this is actually a very similar situation to the methane molecule, CH4. So in this case, in order for the electron pairs to all mutually repel one another, the water molecule adopts a bent structure with the other points of the tetrahedron occupied by the lone pairs on the oxygen. So since there are 4 electron pairs, they form a 109-degree angle with one another. In the case of methane, it is 109 degrees, but in the case of water, it's approximately 109 degrees because there is a slight difference between the hydrogen bonds and the lone pairs due to the presence of slight positive charge from the hydrogen atom. Now, if you have 3 electron pairs and 0 lone pairs, then the molecule will be trigonal planar. If you have 3 electron pairs consisting of 2 bonds and 1 lone pair, the molecule will be bent. Now, if you have 4 electron pairs and consisting of 4 bonds and 0 lone pairs, the molecule will be tetrahedral. If you have 3 bonds and 1 lone pair, that's something called trigonal pyramidal. So it still forms the tetrahedral on the bottom, but then the 4th point of the tetrahedron is occupied by a lone pair. And then if you have 2 bonds and 2 lone pairs, then that is a bent structure. If you have 5 electron pairs consisting of 5 bonds and 0 lone pairs, this will be something called trigonal bipyramidal, which we just discussed. And if one of those bonds is instead a lone pair, it's something we call the seesaw structure, because we like to have fun in chemistry. Then there is the case of 6 electron pairs. If you have this contained within 6 bonds with no lone pairs, it is an octahedral geometry. And sometimes you have strange molecules like xenon tetrafluoride, which has the fluoride atoms in a plane, also known as the square planar arrangement, and then the 2 lone pairs are up top and bottom. So to summarize, if the central atom has 2 bonds and no lone pairs, the shape will be linear. If it has 2 bonds and 1 lone pair, it will be bent. If it has 2 bonds and 2 lone pairs, it will also be bent. If it has 3 bonds and 0 lone pairs, it will be trigonal planar. If it has 3 bonds and 1 lone pair, it will be trigonal pyramidal. And if it has 4 bonds and no lone pairs, it will be tetrahedral. Now, we will introduce the idea of electronegativity and its relation to the polarity of molecules. Now, electronegativity is the ability of an atom in a molecule to attract bonding electrons towards itself. And the higher the electronegativity of an atom, the greater its ability to attract electrons. Fluorine is the reference element for this scale. It is considered to be the most electronegative atom and is given the value of 4. Francium, which is on the opposite bottom corner, is the least electronegative atom. Electronegativity generally increases across a period from left to right on the periodic table and decreases down a group from top to bottom on a periodic table. And as the electronegativity difference increases between 2 elements, so too does the bond polarity. In general, nonmetals have higher electronegativity values than metals because metals tend to lose electrons and nonmetals tend to gain electrons when an ionic bond is formed. Here is a pictorial description of what I just said. Fluorine is here at 4. All of the nonmetals have fairly high electronegativities. The metalloids have intermediate electronegativities, and the metals all have lower electronegativities. And you see the electronegativity is decreasing down the group and increasing across the period. So, bond polarity. Covalent bonds generally involve pairs of electrons shared between 2 atoms and therefore have to be less polar than ionic bonds, which involve a complete transfer of electrons. How equally or unequally these electrons are shared depends on the electron donating or receiving power of the individual atoms, which is measured by their electronegativity. A nonpolar covalent bond is formed between 2 identical atoms because they share the bonding electrons equally, having an equal attraction to them. A polar covalent bond is formed between 2 different atoms because they do not have exactly the same electronegativity and therefore will not share the bonding electrons equally. One atom will always have a greater attraction for the shared pair than the other atom. So, electronegativity increases across a period, it decreases down the group, and the larger the difference in electronegativity makes the more polar molecule. And the negative end of the polarity will be pointing towards the more electronegative atom. Here are 3 examples. Oxygen. It has an electronegativity of 3.5 and an electronegativity difference of 0, making it a pure covalent bond. Carbon monoxide. Carbon has 2.5 and oxygen has 3.5. The electronegativity difference is 1, and this is a polar covalent bond. Now, magnesium oxide. Magnesium has an electronegativity of 1.2, and oxygen has 3.5, making the difference 2.3, and this molecule is ionic. So, when a molecule is polar, then this means that one of the 2 atoms has a greater attraction for the shared pair than the other. This causes the molecule to have a permanent charge discrepancy called an electric dipole. This is when one end of the molecule is slightly positive and the other end is slightly negative. Polar molecules in general have a partial positive charge on one or more atoms. In this case, for the water molecule, it's hydrogen, and then the other atom will have an equal and opposite negative charge. So since we have a partial positive charge on both hydrogen atoms, the partial negative charge on oxygen will be twice that. And because the hydrogen atoms are pulling the oxygen is pulling electron density through each of the hydrogen bonds, the center of the positive charge is located somewhere between the 2 hydrogen atoms, and the center of the negative charge is somewhere in the vicinity of the oxygen atom. So, oxygen, I just said that, pulls the electrons closer to oxygen, partially withdraws them from hydrogen. And the dipoles do not cancel each other. They actually reinforce each other in one direction, which is indicated by the direction of the arrow. And therefore, water is a polar molecule. Now, there are a number of attractive forces at play between and within compounds. There are intermolecular forces, such as ionic compounds, which are bonded together by alternating positive and negative charges. And then neutral molecules are capable of existing freely, and therefore, in order for them to be attracted to one another, they have to have forces that exist between individual molecules. These take the form of dipole-dipole interactions, hydrogen bonding, and what are known as dispersion interactions. And we'll talk about each of these 3 in turn. So the first one is dipole-dipole interactions. So we just talked about polarity and the existence of dipoles. So if one end of a molecule is positively charged and another end is negatively charged, then that means other molecules of the same type can stick to one another because of the mutually attractive force between positive and negative charges. Because these dipoles are permanent, then this doesn't disrupt the overall electron configuration very much. And these stick together somewhat like magnets. Another attractive force is called hydrogen bonding, and this is sort of a special case of dipole-dipole interactions. This occurs between molecules that have a hydrogen atom bonded to fluorine, oxygen, or nitrogen. These all have lots of lone pairs on them and are especially capable of attracting hydrogen, which forms a stronger electrostatic bond, which verges on a chemical bond, which is why it's called a hydrogen bond. And you can see it represented here. The hydrogen atom is partially positively charged. The oxygen atom is partially negatively charged and also has 2 lone pairs of electrons, and so the positive charge feels that negative charge and forms a weak bond. And then the third type of force is called dispersion or London dispersion forces, because they were discovered by a guy named London. These are short-lived dipoles that are caused by uneven shifts in electron density. So say that you have a diatomic molecule such as oxygen, and 2 of them come near each other and their electron clouds bump into one another, and they repel each other, but since electrons are a lot lighter than the positively charged nucleus, the electrons move away faster than the positively charged nucleus can, and therefore the nucleus is partially exposed, and that positive charge might feel the electron cloud from another molecule and attract it, and this ripple will move throughout the substance and cause slight attractive forces between the molecules. For nonpolar substances, this is the only type of intermolecular force possible. And the more electrons present, the easier it is in general to cause them to polarize. And these 3 different attractive forces lead to stronger or weaker interactions between particles. So a nonpolar covalent molecule will have very low heats of fusion and vaporization because it doesn't take as much energy to cause the molecules to move apart from one another. Benzene is another example. Polar covalent molecules are generally a little bit more difficult to melt and vaporize. However, the increasing level of polarity causes these numbers to be higher. So acetic acid is kind of polar. Ethanol is kind of polar and has the ability to form hydrogen bonds. Ammonia has even more polarity and ability to form hydrogen bonds. Water is also quite polar and the ability to form 2 hydrogen bonds per molecule. And then some ionic compound like sodium chloride has an incredibly high heat of fusion and an astronomical heat of vaporization because the molecules are bonded together by raw positive and negative charges. This brings us to the end of covalent compounds. There will be a quiz posted later in the week, as well as a interactive simulation-based electronic structure lab that will be also posted later in the week. I hope everybody was able to finish the exam and is finding the quizzes to be manageable. This week's quiz will cover both this week's lecture and last week's lecture, and next time we will move on to some descriptions of chemical reactions. Have a good night, everybody, and stay safe.